In this video, we present our work in meta-learned real-time dynamics model adaptation for high-speed, off-road autonomous driving. We successfully validate our approach in both a full-scale real-world demonstration and simulated experiments. High-speed, off-road autonomous driving demands precise control over vehicles navigating unpredictable terrains like sand, snow, and vegetation, as well as varying terrain conditions like wetness, deformability, and roughness. Terrain variability can drastically alter vehicle dynamics, making accurate modeling critical yet challenging. Dynamics models used in model-based control often fail to generalize to unseen terrain, necessitating real-time adaptation for maintaining performance and safety. To navigate safely around obstacles, we use Model Predictive Path Integral, or MPPI control, a sampling-based model predictive control method. MPPI works by rolling out sampled control sequences on a dynamics model to generate trajectories. These trajectories are then used to determine the optimal path forward. Because the MPPI process depends on the dynamics model, an accurate dynamics model is crucial for predicting accurate rollouts for the optimization process. Terrain vehicle interactions are difficult to model due to complex and evolving conditions. Learned models are effective on known terrain, but struggle to generalize on unseen environments without adaptation. To address these challenges, we propose a novel framework that combines a Kalman filter online adaptation scheme with meta-learned parameters. In our approach, a learned model predicts residual tire forces, which are then input into a parametric model to generate dynamics predictions. To facilitate online adaptation, we create an ensemble of the last layer of the learned model. Each of the matrices making up the ensemble are weighted and combined with a bias to form the final prediction for the parametric model. We use a Kalman filter to update the adapted parameters, which are corrections to the ensemble weighting and bias, in real time. To perform offline meta-learning, we begin by splitting collected data into trajectory segments containing an adaptation period and an actual rollout period. For each trajectory segment, we run our online adaptation algorithm on the adaptation period of the segment to adapt the dynamics model, which is then used to generate a forwards prediction. A loss is then computed between the prediction and the actual trajectory. We backpropagate through the entire prediction and adaptation process to meta-learn model and adaptation parameters which optimize online adaptation. Specifically, model parameters are optimized to determine the best directions in parameter space along which adaptation occurs, and the Kalman filter parameters are learned to optimize the rate of adaptation that governs how quickly parameters are adapted to changes in the environment. We validate our approach with a full-scale, real-world demonstration where an autonomous vehicle has to safely complete 3 laps around a virtual figure-8 type track. We test our method against a baseline without any online adaptation or meta-learning. This is a 1-lap segment of a run with the baseline configuration. The car takes this turn too wide, causing it to go out of bounds. Poor predictions from the dynamics model causes poor planning, leading to unstable trajectories and course boundary violations. Here, the car briefly goes out of bounds again. The car then plans this U-turn poorly, causing it to get stuck and perform a costly backup maneuver that wastes time. This is a 1-lap segment of a run using our method. Here we see that the car smoothly traverses the track without violating track boundaries or getting stuck. An inaccurate dynamics model can lead MPPI to generate flawed trajectories that fail to account for real-world dynamics. Our method adapts the model to unexpected dynamics, reducing model mismatch and enabling MPPI to generate control sequences that balance performance and safety. We also run extensive experiments in simulation. Here is part of a run using our algorithm on a procedurally generated map with steep inclines and dense obstacles. The graph on the top right displays the norm of the adapted parameters in real time. On the bottom right, the red curve is the prediction error of the model without adaptation, and the blue curve is with meta-learned adaptation. The model was trained only on real-world data, producing a real-to-sim gap when evaluating in the simulator. This is why the red curve displays large prediction error. On the other hand, our approach adapts the model to bridge the real-to-sim gap, resulting in much lower prediction error. For more details on both the simulated and real-world experiments, please refer to the paper.